Hi, today we're going to look at calculating the volume of a solid of revolution by the second method, which is by washer. And again, to give you an idea, I actually kind of showed you last time a situation where that will occur. Let's suppose this is my area, and if you remember, if I were to rotate this about the y-axis, I ended up something that looked like this kind of situation. Again, forgive the drawing, but something of this nature, with my axis right to the middle. Something of that nature. And if this case, if I take my rectangle that gets rotated and make it perpendicular to the axis of rotation like I did before, notice in this case, the rectangle does not go all the way to the axis everywhere. And so when I rotate this, rather than get a circle like I had before or a disc, this time I get something that has a hole in the middle. And because of that, we call this a washer. Not the kind that you do wash your clothes in, but the kind that you put a bolt through. It basically is a disc with a hole in the middle, a disc taken out of it. It's a disc with a disc taken out. And so because of that, given that this is kind of the situation, it makes sense, or should make sense if you think about it, that the volume using the washer method has the form pi integral r sub o squared minus r sub I squared, where r sub o represents my outside radius, the radius to the outside function, and r sub I represents the radius to the inside function. Again, I don't really need the three-dimensional curve, three-dimensional representation, picture. I can look at the two-dimensional, and it tells me what I need, because the distance in this particular case to the outside function would be the distance from the axis to, in this case, because my rectangles are sideways, the distance to the one further to the right, the distance to the inside function is the one to the left. And so that's how we can determine our outside and inside radius. Let's look at some examples. I'll leave that for the moment. Suppose I have y equals the square root of x minus 3, y equals 0, x equals 7, and now about the y-axis. This is the same area that we saw the first example last time, except now, rather than rotating this about the x-axis, which gave me discs, I'm going to rotate this about the y-axis. And if I again draw my rectangle perpendicular to that axis, this rectangle does not go to the axis always, so that's going to give me a washer. My volume, pi integral basic form, r sub o squared minus r sub I squared, outside radius squared minus inside radius squared, the circle taken out from a circle, basically. In this case, my rectangles are now moving up. The rectangles are always perpendicular to the axis. That's the variable that we use. So in this case, since my rectangles are going sideways, the variable that we need is y. and y will go from y equals 0 to the y value at this top corner. And since that occurs when x is 7, that means my y value is 2. And so this goes from 0 to 2. Oops, let me put it on down here. Y goes from 0 to 2. My outside radius would be the distance to the outside function, in this case furthest to the axis, which is this line here. This was the curve x equals 7. And so it is just 7 squared minus the inside radius would be the distance to the parabola, sideways parabola. That would be the curve y equals x, the square root of x minus 3, but I cannot put square root of x minus 3. The variable we need is y. That's why it's kind of useful to write what variable you're dealing with. So therefore, this becomes y squared plus 3 is equal to x. When I solve for x, square both then sides and then add 3. And so this then becomes y squared plus 3, quantity squared. And then we can multiply this out, etc., finish it. I'm going to forego doing that. Again, executive privilege. Next example. Let's suppose I have x equals y squared plus 6 and x equals 5y. And I want to rotate the area between these curves about the y-axis. So x equals y squared plus 6 is a parabola, but it is shifted. Now it's going sideways and actually shifted to the right. It looks something like this. And x equals 5y. This would be y equals 1/5 x if I switch it around, and so that is a line that looks like this. And so this is the area that I want, this piece up there. If I want to rotate this around the y-axis, my axis of rotation is here. If I draw my rectangle perpendicular to that axis, then we end up with rectangles that look like this, which means that I have to use the shell. I have to use the washer. So my volume is pi integral r sub o squared minus r sub I squared. Now, we need the points where these rectangles slide from to, where they start, where they finish. And for that, I have to do some algebra. We need to know where these two curves intersect. So y squared plus 6 is equal to 5y, or y squared minus 5y plus 6 is equal to 0, y minus 2, y minus 3. So these intersect at y equal 2 and y equal 3. This value would be y equal 2. This is obviously not drawn to scale, and this would be at y equals 3. So my volume then is pi times the integral from y equals 2 to 3. My outside radius is the distance to the one further to the right, the line. X equals 5y. Notice this is already in terms of y. My variable that I need is y. That's good. We don't have to do anything. Inside radius would be the distance to the parabola. Parabola is y squared plus 6. And again, we can calculate this, multiply out, etc. take the antiderivative, put in the values, use FDC2, and get the volume. I am going to forego doing that. I will leave that. My last example with washers, I actually want to take this same curve, but I'll redraw it. And same area. And this time, rather than rotating this around the y-axis, we're going to rotate it around the x-axis. So remember, my curve looks something like this. My area looks something like this. And now I want to rotate this around the x-axis. If I make my rectangles perpendicular to the axis of rotation, again, I'm going to get a washer. Now, we need the x values for these points of intersection. I found previously, I'm going to skip some of the algebra here, y squared plus 6 equals 5y. We solved this. I got y equals 2, y equals 3. And so notice, when y equals 2, this means that x is equal to 10. Put it into either one of the two functions, and we get x equals 10. When y equals 3, we get x is equal to 15. And so now my rectangles are sliding across. The variable is always perpendicular to the axis, perpendicular to the rectangle. The rectangle is vertical. The variable that we need then is x. And so x is going to go from 10 to 15. And my volume, in this case, is going to be, again, I'm still using washers, pi r sub o squared minus r sub I squared. My variable is x, goes from 10 to 15. My outside radius would be the distance to the outside curve, which is the parabola. However, we have to have the function in terms of x. And so I've got to rewrite this. So y is going to equal the square root of x minus 6. Subtract 6, take the square root. I get what y equals. And similarly, this one, y is equal to 1/5 x. So my outside radius, the parabola, would be the square root of x minus 6, quantity squared, inside radius, 1/5 x, quantity squared. And again, multiply this out, etc. Make sense? So that takes care of washers.